This video is about relations, not human relations, mathematical relations. You have been using relations of numbers since your first days at school. In particular, equalities and inequalities are so integrated in your brain that it's hard to accept that they are arbitrary and there is a need for justification. Hence, in this video, I will spend my time to explain how we introduce such relations. For that matter, let's answer the question, what is a relation? A relation are between the elements of the sets S and T. More correctly, a relation from the set S to the set T is a subset of the Cartesian product S times T. Obviously, this is not what you were told in your early days of schooling, when you wrote expressions like 3 is strictly less than 5. But let's think for a moment. If you take the set of natural numbers n, the Cartesian product n times n contains all pairs x, y of natural numbers, which we represent as the integer points of the first quadrant when a coordinate system is introduced on the plane. The diagonal of the quadrant contains all points with equal coordinates. Hence, the subset are the Cartesian product n times n that contains all points above the diagonal defines the relation x strictly less than y for natural numbers. If R is a relation and the pair x, y is an element of R, it's more convenient to write xry and read x is related to y by the relation R, or simply x relates to y. A relation is the most basic way to establish connections between sets. Depending on additional requirements we may place on it, we can reproduce other known concepts. For example, a function from the set S to the set T is a relation such that each element of S is related to exactly one element of T. Recall that a binary operation on a set S is a function from the Cartesian product S times S to S. Hence, it can be seen as a relation, a subset of the triple Cartesian product S times S, such that all pairs of elements x, y are mapped to exactly one element of S. Relations, exactly as described, are very common in everyday life, although we do not pay attention. For example, when we watch the weather forecast on TV, or when we check a weather app for the latest information, we're given a relation between the set of locations and a set of numbers. The latter set may represent temperature, wind speed, rain precipitation, or any other quantity of interest. When a map is colored with the flags of the countries, a relation between the set of countries and the set of flags is established. In this video, I will discuss two important kinds of relations: equivalence relations and ordering relations. Both are encountered extensively in math and sciences. They are relations between the elements of the same set. An equivalence relation on a set S is a relation between the elements of S such that it satisfies three properties. 1. The reflexive property, which requires that every element x of S relates to itself. 2. The symmetric property, which requires that if x relates to y, then y relates to x. 3. The transitive property, which requires that if x relates to y and y relates to z, then x relates to z. Notice that all elements must satisfy the first property, but it's not necessary that all possible combinations of elements satisfy properties 2 and 3. In fact, by the very nature of the relation, some elements will relate and some will not. Given an equivalence relation on a set S and an element x, then the set of all elements which are equivalent to x is called the equivalence class of x, and it's indicated by enclosing x between square brackets. Any two equivalence classes, either they're disjoint or equal. Hence, the equivalence relation partitions the entire set into disjoint subsets of equivalent elements. The set of all equivalent classes is called the quotient set of S by the relation. The notation is that of a fraction. There is an obvious surjective map from the original set S to the quotient set, which maps any element of S to its equivalence class. This is known as the canonical or natural surjection. Before I continue, let me introduce some notation. You know, of course, that a function f from S to t is indicated by an arrow pointing from S to t. A surjective function is indicated by an arrow which has two heads. An injective function is indicated by an arrow that has a tail in addition to the head. Finally, a bijective function which is both surjective and injective, is indicated by an arrow which has two heads and a tail. Based on the previous explanations, the natural surjection from a set endowed with an equivalence relation to its quotient set can be indicated symbolically as follows. You know various equivalence relations and classes quite well, even if you never call them as such. 1. Congruence in geometry is an equivalence relation. Each equivalence class includes all congruent shapes. 2. Similarity in geometry is an equivalence relation. Each equivalence class are the similar shapes. 3. Equality of rational numbers when written as fractions of integers is an equivalence relation. Each equivalence class includes all fractions which have the same value. 4. Equality of angles on a trigonometric circle is an equivalence relation. Each equivalence class includes all angles differing by multiples of full circles. Besides the previous examples that are well known, let me show to you another equivalence relation which may surprise you because it makes you rethink what you assumed is obvious. Consider the set of non-zero natural numbers endowed with the operation of addition. This is an abelian semigroup. That is, the operation is associative and commutative. The operation also has the cancellation property. For pairs of non-zero natural numbers, we define the following relation. As written, this relation is unintuitive, but think as follows. If opposite numbers were existing, the two pairs are equivalent if x minus y equals s minus t. That is, if the difference between the two numbers in each pair is the same. But opposite numbers do not exist, so this statement is meaningless at the moment. The relation is automatically reflexive and symmetric. Using the cancellation property, it is quite easy to check that it's also transitive. Hence, it's an equivalence relation. Notice now that all pairs, n, n, are equivalent. Then, given a natural number n, all pairs, x, y, with y equal to x plus n, are equivalent. Similarly, given a natural number n, all pairs, x, y, with x equal to y plus n, are equivalent. Taking all these equivalence classes together, they form the quotient set. So far, so good. Hear the big leap now. I will drop the equivalence class notation and indicate the classes 1 plus n, 1 simply by n. These classes have reproduced the set of natural numbers. But we have more. I will indicate the class of 1, 1 by 0 and the class of 1, 1 plus n by minus n. We have found a way to define the neutral element of addition and the opposite elements to extend the natural numbers to the set of integers. In other words, the quotient set is the set of integers. We can endow it with the operation of addition, where the addition of any two integers is defined through the addition in the quotient set, which in turn inherits the properties from addition among the natural numbers and the equivalence relation. As a result, we have given Z an abelian group structure. As Leopold Kronecker emphatically stated, God made the positive integers. All else is the work of man. Now, let's return to general statements about equivalence relations. Consider a function f from a set S to a set T. I will assume that f is surjective. Otherwise, where it's necessary, instead of the codomain T, we can use the range f of S. Using f, we can always define a relation among elements of S. The elements x and y of S are related if their images are equal. The relation is reflexive, symmetric, and transitive. Therefore, it is an equivalence relation. An equivalence class consists of all elements of S which are mapped to the same element of T. As was stated previously, an equivalence relation gives rise to a canonical surjection. Then we define the function g that maps the class of an element to the image of the element under F. This function is injective, since if the images of two elements are equal, then the elements must be equal too. It's also surjective. As a result, g is bijective. Finally, we notice that the composition of g and the canonical surjection is the original function f. We have thus shown the following theorem. If f is a surjective function from S to t, then there is a unique bijective function g from the quotient set, S over the relation defined by f, to T such that the composition of G and the canonical surjection is the function f. On the screen, I showed you the theorem using a diagram which includes the three functions f, g, and phi. Such diagrams are known as commutative diagrams and are very popular among mathematicians. The more abstract algebra you do, the more you're going to encounter them. They are called commutative since if you start at the origin, you can follow different paths to reach the end, and the result for all paths is the same. Now, let's move to ordering relations. Although not easy to realize immediately, the backbone of equivalence relations is the symmetric property. Remove this property and the entire flavor of the relation changes drastically. In particular, ordering relations replace the symmetric property with its antithesis, the antisymmetric property. A relation on a set S is antisymmetric if for all pairs x and y. The statements x relates to y and y relates to x imply that element x is the same as the element y. Hence, a relation on the set S is an ordering if the relation is reflexive, antisymmetric, and transitive. An ordering on the set S is a total ordering if for all pairs of elements x and y, either x relates to y or y relates to x. I will indicate an ordering relation by the standard inequality symbols and I will use customary terminology less or equal, greater or equal, lower bound, upper bound, supremum, infimum, etc. However, what is exactly meant by these terms depends on the particular definition of the ordering. There are orderings that are drastically different from the standard less-greater relation. Similarly to algebraic structures, which are sets endowed with binary operations, a set endowed with an ordering is called ordered structure. Given a relation R on a set S, we define the reverse relation such that x reverse relates to y if y relates to x, and vice versa. Notice that the reverse of a reverse relation is the original relation. If the relation R is an ordering, then the reverse relation is also an ordering. The reverse ordering of the less or equal ordering is the greater or equal ordering. The following statement, known as the trichotomy law, is true for a total ordering. An ordering on a set S is a total ordering if for all pairs of elements x and y of S, either x relates to y, or x reverse relates to y, or x equals y. A well-ordering on a set S is a total ordering such that every non-empty subset of S possesses a smallest element. Our familiar ordering on the set of integers is a well-ordering. However, on the set of real numbers, it's not a well-ordering. Any open interval on the left does not have a smallest element. For example, for any x in the interval 1, 2, the midpoint of 1 and x belongs to the interval, and it's smaller than x no matter how close x is chosen to 1. Given an ordering on S, for any subset E of S we define, an element U of S is called an upper bound of E if all elements of E are less than or equal to U. If E has an upper bound, is called bounded from above. The least of all upper bounds of E is called the supremum or least upper bound. Similarly, an element L of S is called a lower bound of E if all elements of E are greater than or equal to L. If E has a lower bound, is called bounded from below. The greatest of all lower bounds of E is called the infimum or greatest lower bound. A set is called bounded if it is bounded from above and below. The following theorem is an immediate consequence of the definitions. A non-empty subset E of an ordered structure can have at most one infimum and one supremum. For example, if S and S prime were two suprema, then they have to satisfy the direct and inverse relation at the same time, which imply that S equals S prime. Similarly to homomorphisms and isomorphisms between algebraic structures, we could define mappings between ordered structures. In fact, having ordered structures allows us to duplicate all ideas which relate to monotone functions in the set of real numbers. A function f from S to t between the two ordered structures S and t is called increasing if for all pairs x and y belonging to S, it preserves the ordering. Decreasing if for all pairs x and y belonging to S, it reverses the ordering. Monotone if it's increasing or decreasing. Monomorphism if it's injective and preserves the ordering. Isomorphism if it's bijective and preserves the ordering. Strictly increasing if for all pairs of distinct elements x and y belonging to S, their images are distinct and ordered the same way. Strictly decreasing if for all pairs of distinct elements x and y belonging to S, their images are distinct and reverse ordered. Strictly monotone if it is strictly increasing or strictly decreasing. Exactly as in real analysis, we can use the previous definitions to prove statements for the behavior of the function f under various conditions. For example, if S is a totally ordered structure and T an ordered structure, then a strictly monotone function f from S to T is injective. A function from S to T is a monomorphism if and only if f is strictly increasing. You can now take your calculus book, look at any theorems related to monotone functions you like, and try to translate them in the new abstract scenario. And with this suggestion, I have now finished my presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.